This is 3.3, Rates of Change in the Natural and Social Sciences, Content Objective 2, which is to use derivatives in other disciplines. For our first example, the volume of a growing spherical shell is given by volume equals 4/3 pi r cubed, where r is measured in micrometers. I want to find the average rate of change of the volume of the cell with respect to its radius as r changes from 5 to 5.1 micrometers. So to do this, we are going to look at the fact that the average rate of change is a secant slope. So our secant slope is going to equal V evaluated at 5.1 minus V evaluated at 5 over a 5.1 minus a 5. So we can use our calculator to compute this, and we'll put this into y1. Notice that in the calculator I have put 4/3 pi x cubed into y1, and now on the home screen I can compute that secant slope, which will be y1 of 5.1 minus y1 of 5. Close the top. Now I'm going to divide by the 5.1 minus the 5. Close that parenthesis, hit enter, and we get 320.484. So this will equal 320.484. And let's think about what that is unit-wise. It's a rate of change. Volume was measured in micrometers cubed. And then the radius was measured in micrometers. So how would we interpret this? We would say when the volume was already 5, we are approximately increasing the volume of our cell at 320.484 micrometers cubed per every micrometer of growth in the radius. With part B now, we want to find the instantaneous rate of change of V. So in this case, we're looking at V prime of r, and then we'll plug in the 5. So I've got to take the derivative of this, which means I move through the constant, and then I hit the power. If I now want to evaluate this at 5 micrometers, that means I'm going to plug in a 5. So I get 25, the 3's will cancel, times 4 gives me 100 pi, which is going to be 3.14-ish, so it'll be a little bit smaller than that rate of change we got up on the average. Last part C, we want to explain why it makes sense that the rate of change of the volume of the sphere with respect to its radius is equal to the surface area. So that's a little funky to think about, and let's think about why that would make sense. If we have a sphere and we want an instantaneous rate of change, so that means we are adding just the slightest immeasurably small layer, or we're creating an increase in our radius that is really, really tiny. And when we do that, we're essentially adding a layer of paint to that sphere, which means we are increasing the volume by that surface area. So notice that that volume's derivative, if we actually simplify it, gives us that 4 pi r squared, which is the surface area of the sphere. With example 2, we're dealing with a tank that holds 5,000 gallons of water, and it's draining from the bottom. It takes 40 minutes to drain completely, and we can model the volume of water that is in the tank at any time in that interval using Torricelli's law. So the first thing we want to do is find the rate at which water is draining from the tank. So in order to do that, we need to look at the volume, and we have to multiply it out. So we'll have 1 times 1, then we'll have a 1 times this and double it, so that's a negative t over 20. And then we'll have this thing squared. That's a t squared over a 1600. So if I want to get the derivative, I can move through the constant and then multiply by the derivative of the inside. Well, the 1 as a constant disappears. This would be a negative 1 over 20, and the next one will be 2 over 1600, which is 1 over 800, times t. So we want this to now be our v prime, and we want to evaluate it at 4 different times. So to do that, we're going to go put in this v prime into our y editor. That way it'll be really easy to plug things in. Notice that in y1 I've put in the 5,000 times that negative 1/20th plus 1 over 800 times x. I have to use an x when I'm in the y editor. So now that we have that in, we can go to our home screen and evaluate y1 at 5. We'll do a diamond enter and get a negative 218.75. That's going to be measured in gallons per minute. Now notice that it's negative because the volume is decreasing. We have a negative rate of change in the water volume. So if I want that same thing evaluated at 10, I will do y1 of 10. Diamond enter. We get a negative 187.5. Again, it's gallons per minute. And again, it's negative because the water is draining and the volume is decreasing. We can do y1 of 20. That's a negative 125. And last, we'll do it at 40. Now we could predict what happens at 40 simply because we know it takes that long to drain the tank. So we should end up with 0. So at what time is the water flowing out the fastest versus at what time is the water flowing out the slowest? We can see that it's the slowest when it's not flowing at all. So that's going to happen when time is 40 minutes. So to get it at the fastest, we can see that we are decreasing as time goes on, the rate at which the water's flowing out. So I would anticipate that the maximum rate of water flowing out would occur right when we pull the plug. So that would be at the very initial time. So if we were to plug in a time equals 0 here, we can see that we're going to get a negative, 250, which is definitely going to be a faster water flow than at 5 minutes. With example 3, we again are dealing with a data version or a numerical version of a problem. And we have a chart here that represents the year and the age at which Japanese women are getting married for the first time. So if we want to estimate the rate of change of a Japanese woman's age for her first marriage in the year 1990, we're looking for a prime at 1990, and we're going to approximate it by locating 1990 and then using the flanking points. So we'd have a 26.3 minus a 25.2 over a 1995 minus a 1985. Well, that's going to give us a 1.1 over a 10, which is a 0.11, and we're measuring it in age measured in years versus the date measured in years. So what that means is in 1990, the rate at which Japanese women were marrying was increasing at 0.11 year per year. With example 4, we're dealing with a chemistry application. We have one molecule of a product C getting formed from one molecule of the reactant A and one molecule of a reactant B, and we're given the initial concentrations of A and B that are both written as these bracket A and bracket B, and it's measured in moles per liter. So first we want to find the rate of the reaction. So here's this rate of the concentration of C is depending upon the time. So we are going to find the rate by taking the derivative of that concentration. Low D high minus high D low over the low squared. So this is a little tricky for some people because we have to remember what are constants and what are variables. K is a constant, A is a constant, and T is the variable because this is all depending upon the time T. So if I take the derivative of the low, I'm going to get the constant coefficient for T, which is AK. Or excuse me, the low D high, I've got to take the derivative of the high. So the low will be AK, and the top will be A squared K, because this is the coefficient of the T. So it's just a number, and the derivative of that number times T is just the number itself. If I care to simplify this, I will get an A cubed K squared T plus an A squared K minus an A cubed K squared T all over that AKT plus 1 quantity squared. Notice that these two cancel, so I'm left with just an A squared K over an AKT plus 1 quantity squared. So what happens to the rate of the reaction as T goes to infinity? So that's asking me what is the limit as T goes to infinity of that concentration's derivative? And we'll end up looking at this as T gets huge. Well, as T gets huge, the denominator is going to far, far outpace the numerator, which is just a constant. So that rate of reaction will be 0. Why does that make sense? Well, if you dump two reactants together, they may bubble away for a while, but eventually everything that can react will react, and there won't be anything left to react. So that rate of reaction will end up being nothing. What happens to the concentration? Well, on this one, we're looking at the limit as time approaches infinity on the original concentration function. If we look at that, we've got a dominant term of AK, or A squared K times T on the top, and if I look at the dominant term on the bottom, I get an AKT. Reduce that. The T's cancel, the K's cancel, and one of the A's cancel, and I end up with a limit of A, which kind of makes sense because I started with A and B that both had concentrations of A, and I use every mole of this and every mole of this to make the same number of moles of C. So that concentration of C is going to be the same. I'm going to have the same number of moles of C as I had initial moles of A and B. The last example, example 5, is an economics variation of this theme. So we're looking at rates of change as we are producing washing machines and then selling them. So the cost of producing X washing machines is given by this function. I want to find the average cost of producing 100 washing machines. So where most people mess up with this part A is they misread this as the average rate of change in the cost. And I'm not asking for the average rate of change. I just want to know what the average cost is. So this is an old problem, something you might have encountered in Algebra 1 or even in Algebra 2, maybe in pre-calculus, but doubtful because it's just simple. So to find the average cost, we're going to take the total cost of making 100 machines, and then we're going to divide by that 100 machines. So to get that, we're going to do C of 100, and we're going to divide it by 100. So we're going to go to our calculators to do this. So notice here in the calculator in Y1, I have put that cost function 200 plus 100x minus 0.1x squared. So now on my home screen, I can compute Y1 of 100, which is the cost of making 100 machines. And then I can divide that by 100. And I'm going to put diamond enter to make sure I get 92. So I can write here that the average cost is $92 per machine. Part B says find the average rate of change. So now we're looking at a secant slope with respect to x when the production levels changed from 100 to 105. So that average rate of change would be the cost of making 105 minus the cost of 100 over the 105 minus 100. So in this case, we are looking at a secant slope. So again, we'll go to our calculator, and this time we will do y1 of 105 minus y1 of 100, close the top, divide by that 105 minus 100. Diamond enter again, and we get 79.5. The units will still be dollars, because that's how we're measuring the cost per machine, because we've produced these machines. For part C, we want to find the instantaneous rate of change, or the marginal cost, when x is 100. So we're looking at the instantaneous rate of change, which is the derivative, which will be 100 minus 0.2x, and then we want to evaluate that instantaneous rate of change when x is 100 machines. So we'll have 100 minus 0.2 times 100, which is 100 minus 20, or 80. Now the units of this C prime, remember it's a rise over a run, so we had cost, which was measured in dollars, and then we had the number of machines as the horizontal input. So a rise over run, if we have our cost function, rise over run, that slope is going to be measured in dollars per machine. So what does this mean for us? This $80 represents the slope of that line, which means if we go over 1 and make 101 machines, the cost should go up $80. So that takes us to part D, which says show that the marginal cost when 100 washing machines are produced is approximately the cost of producing one or more washing machines after the first 100 have been made. So we've got this $80. We want to show that that is approximately how much it would cost to make the 101st machine if we've already made 100 machines. So if I now compute this on my calculator, we can see that y1 of 101 minus y1 of 100, that's our cost of the 101st minus the cost of doing 100. That'll give us how much it costs just to make that 101st machine is $79.90. So we can see that that marginal cost, or that derivative approximation, was a very good approximation for the actual cost. So finish working on your notes web exam problems, identify the ones you need help with, and then see if you can write at least 2 other real-world applications that weren't in these notes where knowing the rate of change might be beneficial.